we're going to look at this specific question, what's known as the nth roots of unity. So solutions to this sort of equation. Z to the power of n is equal to plus or minus 1, but unity. If you were to plot the solutions, what they will form is a lovely n-sided polygon. And those vertices will end up on the unit circle, because the modulus of all of them will be 1, because we're dealing with unity. So something like this. If we had to solve z to the power of 5 is equal to 1, and we now know we can convert that with de Moivre's theorem, and it would become cis 2 pi k plus 0 over 5. Because I'm dealing with a real number, I'll go with conjugate pairs. So k would be 0, plus or minus 1, plus or minus 2. So they would be the 5 solutions. But mind you, cis 0 I can work out. That would just be, and let's plot it, there it is. Cis 0 would of course just be 1. But we know they're evenly spaced around the Argand diagram. So the next one would be 2 pi and 5. Its conjugates there, so minus 2 pi and 5. Next one, 4 pi and 5. Its conjugate, minus 4 pi and 5. And sure enough, if you were to draw that up, we get a pentagon. And that pentagon lies on the unit circle. So there's our 5 roots of unity. All right, but then we like to ask these sorts of things. If omega is a complex root of, it's the equation we just solved, just written a different way. But show that omega squared, cubed, power of 4 and power of 5 are the other roots as well. But the thing to realise, when they say a complex root, they're talking about the non-real ones. So they're not talking about the solution z equals 1. Because obviously, I suppose when you think about it, if it was equal to 1, well, yeah, your 1 squared's 1, yeah, that works. 1 cubed's 1, that works. And so kind of obvious. So how do we do it? Well, basically, we just play with our index laws. We know z to the power of 5 is equal to 1. But omega is a solution, so therefore we know omega to the power of 5 is equal to 1. Well, omega to the power of 5 to the power of 5 would be 1 to the power of 5, which is 1. So omega to the power of 5 solves the equation. So omega to the power of 5 must be a solution. Now, omega squared, well, we sub that in to the power of 5. I could rewrite that to be omega to the power of 5 all squared. But we've now established that omega to the power of 5 is 1. So that's 1 squared, which is 1. Omega squared solves the equation, so omega squared is a solution. Omega cubed to the power of 5 I could rewrite as omega to the power of 5 cubed. We've established omega to the power of 5 is 1. 1 cubed is 1. Therefore, omega cubed is a solution. You're never going to guess what I'm going to do with omega to the power of 4. Omega to the power of 4 to the power of 5 is the same as omega to the power of 5 to the power of 4. We've established omega to the power of 5 is 1. Therefore, omega to the power of 4 is a solution. Thus, if omega is a solution, or a root, then so is omega squared, omega cubed, omega to the power of 4, omega to the power of 5. Okay, kind of a long way about it. A quicker way of doing exactly the same thing. I could do this. Starts off the same. Z to the power of 5 is equal to 1. We know that. If omega is a solution, then omega to the power of 5 is equal to 1. So again, exactly the same as what I just did. But now I do something clever. If k is an integer, then omega to the power of k to the power of 5 will equal omega to the power of 5 to the power of k. Well, omega to the power of 5 is 1. 1 to the power of k will always equal to 1. So what we're now basically saying is, as long as k is an integer, this will be true. So therefore, omega squared, cubed, 4, 5, 6, 7, 8, 9, 10, it really doesn't matter. It will be a solution. So now we've established that. They love this one. Prove that 1 plus omega squared plus omega cubed plus omega to the power of 4 ends up equaling 0. Well, remember, these are solutions to a polynomial, but you'll notice I don't have 1 there, I have omega to the power of 5, because we've established that omega squared, omega cubed, omega to the power of 4, omega to the power of 5 are the roots. So the sum of the roots will be minus b on a. But in our equation, b is 0. There is no coefficient of z to the power of 4. So these things must equal 0. But hang on, how did I get 1? Oh, that's right. Omega to the power of 5 is equal to 1. We've established that. There's our result. Yeah, that's an okay way of doing it. Here's another way. We start with the actual equation itself. Well, we know how to factorise that. That's omega minus 1 outside of 1 plus omega squared plus omega cubed plus omega to the power of 4. Because remember, when you have the difference of two squares, cubes, quartics, whatever you like, it'll always be the first factor, omega minus 1, second factor, 1 plus omega going up to n minus 1. Well, all right, we want to solve this equation, but we know omega is not 1. Because we said it was a complex one. So it's not the solution omega equals 1. So therefore it must be the other one that's 0. So 1 plus omega squared and so on must equal 0. Yeah, that's an okay way of doing it. But there's a better way. 1 plus omega squared plus omega cubed plus omega to the power of 4. Well, hang on, that's a geometric series. The first term's 1. The ratio is omega, and there's 5 terms. So if I sub it into the formula, look at the top of the fraction. Omega to the power of 5 minus 1. Oh, but that's equal to 0. Therefore, that's 0. Which way do I use? Probably the first one, to be honest, because I think it's the quickest. Sum of the roots, 0, done. So now let's play. We're going to find a quadratic equation. The roots of this quadratic, well, one root's going to be omega plus omega to the power of 4. The other one's going to be omega squared plus omega cubed. Well, what would the sum of the roots then be? Well, the sum of the roots will be omega plus omega to the power of 4 plus omega squared plus omega cubed. But I now know what that is, because we've now established that 1 plus omega squared is equal to 0. Therefore, that must equal negative 1. Okay, product of the roots. Well, let's expand that out. But omega to the power of 5 is equal to 1. Therefore, omega to the power of 6 is omega. And omega to the power of 7 is omega squared. Well, those all added together is negative 1. I now know my equation. X squared minus the sum of the roots, so minus 1. So x plus the product of the roots, negative 1. There's the equation. Basically, when you're playing with these questions, there's only two things you know. You know 1 plus omega squared plus however many you've got is equal to 0. And that omega to the power of n is equal to 1. Using those two facts alone, we should be able to solve anything. Something like this. Omega is a complex cube root of unity. Use the fact so we don't have to worry about proving it. They've given the relationship. 1 plus omega squared is equal to 0. To evaluate this. 1 plus omega squared all cubed. Now, the temptation is to expand the whole thing out. We don't need to. Because 1 plus omega squared must be minus omega. Playing around with 1 plus omega squared is equal to 0. Well, minus omega cubed would be minus omega cubed, and omega cubed is equal to 1. That's negative 1. Algebraic fraction. I need to get a common denominator, but I'll tell you what, I'm not going to use those as my denominator. I'm going to use those. Because 1 plus omega would be minus omega squared. 1 plus omega squared would be minus omega. I've got a much simpler algebraic fraction to play with now. Okay, common denominator will be omega squared. On the top, I get minus 1 minus omega. That's all right, because minus 1 minus omega would be omega squared. Omega squared and omega squared, 1. Now, I don't want you thinking the answer is always 1 or minus 1. It does come up a lot, but it could be other things. Let's find a cubic equation now. The roots are going to be 1 plus omega squared. If I was to factorise it, I know one of the factors is z minus 1, because it's a root. The other one must be z squared minus the sum of the roots, 2 plus omega squared z, plus the product of the roots, and when I expand that out, I get 1 plus omega squared plus omega cubed. Well, what do we know? We know 1 plus omega squared is equal to 0, so therefore 2 plus omega squared must be equal to 1. Okay, I've got 1z. 1 plus omega squared plus omega cubed, well, 1 plus omega squared is 0. Omega cubed is 1. I'm left with 1. There's my equation. Wow, let's expand it out, tidy it up, looks a lot nicer. Z cubed minus 2z squared plus 2z minus 1 equals 0. So those two facts, you can manipulate everything. Solve this equation. So it's about 5 and so on. It's a pentic equation to solve. Well, let's turn it into something easier. Because we know this. Z to the power of 6 minus 1 would be z minus 1 times all those things. Now, I know how to solve z to the power of 6 minus 1 equals 0. They will be the 6 roots of unity. So this new equation I've created would have solution cis 2 pi k on 6, where k is 0, plus or minus 1, plus or minus 2, and 3. Therefore, if I want to solve this equation, it should have the same solutions except the extra one that I've created. Because what I've done is turned it into this. On the top of the fraction, I'll have z to the power of 6 minus 1. But then on the bottom of the fraction, I'll have z minus 1. The z minus 1's cancel, and you'll see I've got the actual equation that I'm playing with. But it can't have the solution z equals 1, because bottom of the fraction would become 0. So therefore, it will be all the solutions of the top of the fraction, excluding the solution z equals 1. Therefore, the other 5 solutions must be the solution to this pentic. And so there are the solutions to the equation. Now, some of these we can work out. Actually, all of these we can work out. They're all exact value ones, aren't they? There are all the solutions to this equation. So playing with the roots of unity. Here's an HSC one, a very old HSC one, mind you, but here it is. We were told that omega is this specific one. So the cos of 2 pi on 9 plus I sine 2 pi on 9. Show that omega to the power of k is a solution. That's similar to what we just did earlier, so I'll do it the same way. So z to the power of 9 is equal to 1. We know that. So z will equal the cis of 2 pi k on 9, where k is. In this case, I didn't bother with conjugates, possibly because I'm saying k is an integer, so I just listed integers. It doesn't really matter. It's sort of like what we did the other day, in that all I need are consecutive numbers. It doesn't really matter which consecutive numbers I pick. Well, by de Moivre's theorem, z equals cis 2 pi on 9 to the power of k. It's sort of using de Moivre's in reverse. I'm taking the power out of the complex number. Well, cis 2 pi on 9, that's what they told me omega is. So omega to the power of k is a solution. The stock standard one, just written a little bit differently. Instead of saying 1 plus da 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 equals 0, they've moved the 1 to the other side. But essentially, it's the same question. So I'll say, oh, well, z to the power of 9 minus 1 equals 0. That's my equation. Therefore, 1 plus da 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 da, sum of the roots. Thank you very much. But now I'll move the 1 over, and I've got the result that they want. Heads show cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9 is 1/8. Well, I know all of the roots. So therefore I should be able to factorise this like so. Z minus 1, Z minus omega, and so on and so on. But you'll notice how I've written them. I haven't just gone power 1, 2, 3, 4 and so on. You'll notice each pair there, I've grouped them such that the two powers add up to be 9. Because basically, they're your conjugate pairs right there. So therefore, when I get z minus omega and multiply it with z minus omega 8, it should be the quadratic minus the sum of the roots. Well, that'll be twice the real part, 2 cos 2 pi on 9, plus the product of the roots. Product of the roots is going to be 1. We're dealing with roots of unity here. Omega times omega to the power of 8 is omega to the power of 9, and we know omega to the power of 9 is equal to 1. That's why I've grouped them together, so those powers will add up to be, in this case, 9. I know that the product will have to equal 1. And I've done the same with each of the following pairs. Now, one of those I can work out exactly. Where is it? 4 pi on 9, no, 6 pi on 9, isn't it? because that would be the same as 2 pi on 3? It's an exact value anyway. There it is, I've done it. So 2 pi, cos of 2 pi on 3 is -1/2. 2 times -1/2, and we get +1. So that one's z squared plus z plus 1. The other ones are those. Now I've got to end up with cos pi on 9 times cos 2 pi on 9 times cos 4 pi on 9. And I got these things multiplied together, but annoyingly, I've got this z squared plus 1, if only that could go away. Well, it can go away if I do a clever sum. What would make z squared plus 1 go away? If I let z equal to I, because I squared is -1. So let's let z equal 1 and see what it now says. I'll get I to the power of 9 minus 1 is I minus 1. The z squareds plus 1 have gone away. But you'll now notice when I expand out, I will get cos times cos times cos, which is what we're looking for. That's the pattern that we want. So, all right, we can do better than that though. I to the power of 9, what's that going to be? I. So we now have I minus 1 is I minus 1 minus I to the power of 4, because notice the other 4 things, there's an I, or there's a minus I times a minus I times an I times a minus I. So bringing that all out, I've got minus I to the power of 4, and I'm left with 2 cos 2 pi on 9, 2 cos 4 pi on 9, 2 cos 8 pi on 9. Well, the I minus 1s will cancel nicely. I'm left with -1. 2 times 2 times 2, that's 8. Almost there. They weren't the ones they wanted, were they? We got 2 pi on 9, 4 pi on 9, 8 pi on 9. What did they want? Pi on 9. Aha. But hang on a sec. Cos of 8 pi on 9, well, 8 pi on 9 is obtuse. Second quadrant, the acute angle, cos pi on 9. So that's the same as minus cos pi on 9. Right, we're almost there. Bingo. The negatives will cancel, divide by the 8, and we've proven it's equal to 1/8. There it is. Oh, what fun was had. 3C, roots of unity.